This video will cover training Lasso models in R. By the end of this video, you should understand how you train Lasso models in R, what methods are available to help you choose a good value of the regularization parameter, lambda, what are good choices for the regularization parameter, and how you create predicted values from a trained Lasso model. The R code shown in this video is available in the learning management system. You'll need the dcelectricity.rds data file. There are several packages that train Lasso models in R. They include LARS, GLMNet, and HDCI. In this course, we're going to use a variant of the most popular package, GLMNet. GLMNet is old and pretty difficult to use. So we're going to use the package GLMNet utils, which adds on to GLMNet and makes it easier to use. We're going to train and evaluate Lasso models in R. You should first install the GLMNet utils package if you haven't already, and then you should load the dcelectricity.rds data file. Before we get started, we're going to divide it into training and test samples using the sample function. So before we get started, I'm going to set up the data files that we need. I'm going to load the GLMNet utils library, which will give me an advanced version of GLMNet to train Lasso models. I'm also going to load the Model R and the Broom library, which will help us interpret our Lasso results after we train models. After that, I'm going to load the dcelectricity.rds data file. And as I showed you before, I'm going to divide this into training and test data using the sample function. I'm going to run all of that now. Looking over in the Environment Explorer, you can see now that I have elect.test and elect.train. I'm going to use the elect.train tibble to train my Lasso models. Training Lasso models with GLMNet builds on a lot you've already learned. Remember, if we were going to train an OLS model in R, we'd use something like this. The LM function, we'd provide a formula, which is a label followed by a tilde, and then a list of features separated by plus signs. As a second argument, we'd provide the data that we'd like to use to train the model. You follow this exact same pattern using GLMNet utils. You'll use the function GLMNet. You'll provide a formula exactly like you would have with LM, and also you'll provide a data argument the exact same way you would have with LM. You might remember from previous videos that Lasso requires you to choose the scale of the regularization parameter, that lambda. You can choose a specific value using the s equals argument. So here in this example, I just add that argument there. But do you need to specify it? If you don't choose a value, GLMNet is going to compute Lasso models for every important value of lambda and save all of them. Due to the mathematics underlying solving the Lasso problem, this is usually faster than solving the Lasso problem for a single arbitrary lambda. So in general, you're not going to choose your own value of lambda. You'll let GLMNet train Lasso models for every important value, and then you'll pick out the value of lambda that you would like after it's trained all of them. This has given us everything we need to get started training Lasso models. So what we're going to do is, using our training data, train both an OLS and a Lasso model with the following formula. This is going to be electricity demand is a function of an 8th degree polynomial of the high temperature, an 8th degree polynomial of the low temperature, and all of the two-way interactions of those terms. This is going to be a really big model. We'll print out the Lasso model object, and then we'll look at the predictions from this model. Looking at my code in R, we're going to use this formula several times, so I'm going to store it in a variable. I'll call that formula.a. After that, I can train a model using OLS, using the LM function. I'll save that in model.ols. Training a Lasso model just requires changing the function from LM to GLMNet. That's what I have here. I'll save that in model.lasso. I'll run all of that and then print out the Lasso model. Looking at the output of the Lasso model, you can see it's a little bit different from what you might get from an OLS model. Importantly, it doesn't print out the model parameters. And this is because GLMNet has trained many versions of this Lasso model with different values of lambda. What the summary at the bottom is showing you is the range of the values of lambda that GLMNet used when it was training Lasso models. Let's go back to my code. I'd also like to add predictions from this model to my original data. That's what I have here. I'll use the Model R function, add predictions. I'm just going to print this result out in the console. I run that. Looking at my results, you can see this has added many variables to my data set. R has added predictions for every Lasso model that it's trained. This winds up being 14 different columns of predictions. You can imagine how this might not be as useful as you'd like. We'll see how to extract the specific predictions that we'd like in just a minute. Before we get to extracting those predictions, let's talk a little bit more about lambda. You'll notice that R trained a bunch of different Lasso models for different values of lambda, but it didn't give us a good idea of which one would be the right one to choose. One way to compare models to choose hyperparameters like lambda is through cross-validation. Cross-validation gives us a sense of how well models might predict out of sample. So you could think we could go through the entire cross-validation process, where we divide our data into cross-validation folds, we train Lasso models for every important value of lambda and make predictions out of sample, and then we choose the value of lambda that led to the lowest average value of the loss function out of sample across all of those folds. This seems like a lot of coding. The fact is that choosing an optimal lambda with cross-validation is so common that it's built into glmnet utils. You can cross-validate models using the function cv.glmnet. It works just like glmnet. You provide it a formula, and you provide it your data. And instead of training just a single set of Lasso models, it will perform cross-validation on your data for a full set of Lasso models. It's going to compute the out-of-sample mean square error for each important value of lambda. After cv.glmnet is done, it identifies two important values of lambda. The first, lambda.min, is the value of lambda that minimizes the out-of-sample mean square error. The second is lambda.1se. This is the largest value of lambda, or the biggest penalty, with an MSE within one standard deviation of lambda.min. Lambda.1se will generally result in a more parsimonious model, a model with fewer features, than lambda.min. But the mean square error out of sample is still close to lambda.min, and so it's usually preferred by data scientists because you still get a low mean square error, but with a parsimonious model. So we can try cross-validating our model. Let's use the cv.glmnet function to train Lasso models using the previous formula on our training data. Then we're going to create a tibble of our model results using the tidy function from the broom package. After that, we'll glimpse this tibble to see what it looks like. Looking at my R code, you can see I'm going to train a model using formula A that we defined before on the elect.train tibble using the cv.glmnet modeling tool. We'll save that result to model.lasso.cv. We can then take a look at this model using the tidy function in the broom package. So we'll run tidy on that trained model. We'll save it to model.tidy so we can use it later, and then we'll glimpse the contents. Let's do that. Looking at my output, you can see this has created a tibble with 6 columns. The first column is lambda. This contains the important lambda values that are identified as it was training models. The second column is estimate. This is the out-of-sample mean square error from each of the models evaluated using cross-validation. std.error is the standard error of that mean square error estimate. But more importantly, are conf.low and conf.high, which are confidence intervals around that mean square error estimate. This tells you how certain or uncertain you might be that if you were to repeat this process, you'd get a trained model that had a mean square error somewhere around estimate. Lastly, the N0 column tells you the number of variables whose values have been forced to be 0 by the Lasso penalty. This tibble of data from the tidy function gives us a nice way to examine how changing the value of lambda in Lasso models alters the mean square error. What I'd like to do is create a visualization. On the x-axis, I'm going to put the values of lambda. On the y-axis, I'm going to put the cross-validated MSE as a line. I'm also going to add a ribbon plot, which is an area plot, with the high and low confidence intervals on the y-axis. It's pretty conventional because both lambda and mean square error tend to have very large ranges to use a log base 10 scale on both axes. So I'll add that to my visualization as well. Looking at my R code, I have some ggplot code to do just that. I'm going to load model.tidy as my data. First, I'll create a ribbon plot that has lambda on the x-axis. The lower y value will be conf.low, and the upper y value will be conf.high. I'll also add a line plot with lambda on the x-axis and the mean square error estimate on the y-axis. I can change the x and y axis scales to a log base 10 scale using scale underscore x log 10 and scale underscore y underscore log 10. Let's run that code and look at the visualization. You can see that for very low values of lambda, low values of the penalty, the mean square error is quite large. As you increase lambda, that mean square error drops. It seems to reach a minimum somewhere between a lambda value of 1,000 and 10,000. Then after that, as you increase the penalty function, the mean square error starts to increase again. You can see that somewhere between 1,000 and 10,000, there should be a value of lambda that's minimizing the mean square error when predicted out of sample. There are a couple of other handy functions for looking at our Lasso models. First, we'll use the glance function from the broom package. It will show us both this lambda.min and lambda.1se values for lambda. Then we're going to display the model coefficients for lambda.min and the lambda.1se models using the coefficients function. Unlike the normal coefficients function, we'll have to tell it which value of lambda we'd like to use. We can do that using the s equals argument. S equals can either be a number specifying the value of lambda, or it can be the text in quotation marks lambda.min or lambda.1se. Looking at my code, First, I'm going to look at what the optimal lambda values are using the glance function. I just supply it with my model that I trained via cross-validation. Let's run that. Looking at the output, you see it gives me three important pieces of information. The first is lambda.min, which is that value of lambda that minimized the out-of-sample mean square error. That's 3,400. Then there's lambda.1se. This is the largest value of lambda that is within one standard deviation of that lambda.min. You see it's 19,916. Finally, the nobs column tells you the number of observations that were used to train the model. Going back to my code, let's take a look at the coefficients from the lambda.min model. We can do that using the coef function. We provided the model, and then we tell it the value of lambda we'd like to use. Here I'm saying s equals lambda.min. Let's run that and look at the output. You can see there are a bunch of rows here. If you remember, we interacted two 8th order polynomials with each other, so there should be 64 parameters to this model. We're only seeing the last few of them here, but we can scroll backwards and see all of them. What you'll notice is that many of the parameter values are just a dot. These are parameters that were forced to 0 due to the penalty portion of the loss function in Lasso. If you were using Lasso for feature selection, you might think features that have 0 parameters should be excluded because they're irrelevant. Going back to my code, we can also look at the coefficients for the lambda.1se value. Let's do that. Looking at the output, again, you see many of these values have been forced to 0. In fact, many more than for lambda.min. This is what you would expect. Lambda.1se places a higher value on the penalty function and therefore forces more parameters to 0. This leads to a more parsimonious model with fewer features. We'd like to make predictions from our Lasso models too. Because both glmnet and cv.glmnet contain many Lasso models, they don't work with add predictions like we expect. So instead, we can add predictions using mutate and the predict function. How might this work? We would take our data and pipe it to a mutate verb. We create some variable name. Here I've just put predvar in brackets to denote the variable name that you might use. We'll use the predict function. It takes 3 arguments. First, we provide a model. Next, we need to provide the data that's used to predict. Since we're piping our data into this mutate verb, you can just use the dplyr shortcut of a period to say use the data that I've piped in as my prediction data. Lastly, we use the s equals argument to set the value of lambda. It can either be a number for a value of lambda, or it can be lambda.min or lambda.1se in quotation marks. Finally, after predict, we have to put a bracket, a comma, a number 1, and then a closing bracket. This is because the predict function returns a matrix, and we only want the first column of it. Doing all of this, we'll add a new column to your tibble that has predictions from the specified Lasso model. So we'll add predictions from our Lasso model to our existing data. We're going to do this for both the OLS model and Lasso models with lambda values of lambda.min, lambda.1se, and a lambda value of 100,000. We'll then create a visualization with predictions from OLS and the lambda.1se model on the x-axis, the actual values on the y-axis, and also a slope 1, intercept 0 line that would represent perfect predictions. So looking at my code, I'm going to take my elect.train data. I can add predictions using the add predictions verb for the OLS model. Lasso requires that I use the predict function combined with mutate. So in these next 3 rows, I create 3 new variables, pred.lasso, .min, .1se, and .100,000. I use the predict function. I provide it my trained and cross-validated Lasso model. I tell it that I would like to use the data that was piped in as the basis of my predictions. And then I tell it the lambda value with the s parameter. Finally, I put a comma 1 inside square brackets to tell R that I would like the first column of the matrix that comes out of the predict function. I'll run all that. This has added some new columns to my elect.train tibble. Now what I'd like to do is create the visualization. I'm always going to put the actual value of demand on the y-axis, so I'll make that as part of the ggplot aesthetics. I'll add a point geometry for the Lasso predictions, a point geometry for the OLS predictions, and a 45-degree line using geom line. Let's run that and take a look at the visualization. Looking at the visualization, the Lasso model dots are the pink color, the OLS dots are the blue color. You can see both models perform comparably well. The OLS dots maybe follow the line a little bit better. But remember, we're looking at in-sample predictions here. What we might like to do is actually predict out of sample and see how well these models perform. The predictions from our OLS model looked pretty good. But remember, we were looking at in-sample predictions. And we should really evaluate model predictions out of sample. So what I'd like to do is repeat the previous analysis using our test data instead of the training data. We'll add predictions for OLS in the Lasso model, and we'll visualize the predictions against the actual values and decide which model we actually prefer. As one additional step, We'll compute the RMSE of both the OLS and the lambda.1se models. Unfortunately, you can't use the RMSE function or other model R functions to compute out-of-sample loss with GLMNet. Instead, we'll use summarize to compute the root mean square error for both OLS and this one lasso model. Looking at my R code, here I just repeat the exact same process we went through before, but instead of using my training data, I use the elect.test tibble. I add predictions from OLS and the lasso models, and then I'm going to create a visualization just like the one we had before. Let's do that and take a look at it. As you can see, this visualization doesn't make a whole lot of sense. What's supposed to be a 45-degree line is straight up and down, but you'll notice there are 3 very extreme OLS predictions. This is a classic result of overfitting, that the OLS model looked like it did quite well in sample, but when it starts predicting out of sample, the predictions start to go down in quality. Here they have gone down substantially. So what I'd like to do is just repeat that visualization, but this time plotting only the predictions from the lasso model. Looking at that visualization, this looks a lot more like what we should expect. The predictions tend to be tightly clustered around that 45-degree line and follow it relatively well. This demonstrates how Lasso can protect against overfitting. Even though we provided the Lasso model with a large number of features, it only used a few of them in the training process, and as a result, the predictions are less likely to be susceptible to overfitting. Going back to my code, the last thing that I'd like to do is compare the root mean square error of OLS to the 1 standard deviation MSE from Lasso. Remember, we can't use the RMSE function to do this, so instead we'll take our data and we'll summarize it, computing the root mean square error manually as the square root of the average of the squared prediction errors. Let's run that. Looking at my output, you can see that the root mean square error of the Lasso model is 191,296, but the root mean square error of the OLS model is 17,484,193. In terms of out-of-sample prediction accuracy, I would far prefer this Lasso model to the OLS model. This again is a good example of how Lasso can protect against overfitting by forcing many of the features in your model to have parameters equal to 0.